Okay, so let's go ahead and get started. Today, we're going to be continuing 3.7 where we last left off. Now, you will notice there's been a small gap between the first part of 3.7 and the second part of 3.7. That's because we've spent the last few days working on graphing. One of the things that I knew heading into this chapter was that graphing is a big deal, and it's been a big deal for the entirety of the chapter. We're at the very end of the chapter. The students are really still struggling on how to build a table, how to fill out an equation, where to plot left versus right, up versus down, and how to read a slope. Things that we really shouldn't be struggling with at this point, but a lot of the kids are, in full honesty, I've got a lot of kids not doing their homework. A lot of kids just aren't taking the class seriously at this point, and it's kind of starting to come to the forefront that they don't really know what they're doing. So today, for good or for worse, we're going to move into the second part of transformations. Now, these are a little more difficult to do than the first part of the transformations. We have reflections, and we have things where we're going to stretch or compress a graph. The word that we're using in this textbook is going to be shrinking. I've never used the word shrinking before, but it's the same idea. You either take a graph and you stretch it vertically, or compress it vertically, or you can stretch it and compress it horizontally. With a line, I do put a bit of a caveat. Lines look like they rotate, and we'll cover that here in a minute. They don't actually rotate, but it looks like they do, and students get a little tied up on that, but the later graphs, much easier. So first thing, reflection. Now what a reflection is we're going to take a graph, and we're either going to reflect it across the x-axis or the y-axis, which means if I have something over here, I'm going to reflect it over there. Or if I have something on the bottom, I'm going to reflect it up. So I'm either reflecting over the y or the x-axis here, or I'm reflecting across the y-axis here. Now later on in later courses, especially in Algebra 2, you'll reflect things across diagonal lines, called an inversion, or you might reflect things across lines that are nowhere near diagonal, they're just other lines. Or you might even reflect things across a curve. And it opens up a lot of questions students might have where they're like, how do you reflect something across a curve? I like to say, think Carnival House like funhouse mirrors. It distorts a lot of things. But in Algebra 1, the two types of reflections we always do are either x-axis or y-axis reflections. That means if it's a y-axis reflection, the y-axis is the up and down, the vertical one, I take my left and my right and I swap it. What was left, it becomes right. What was right, it becomes left. The other is an x-axis reflection. It's reflecting over the x-axis. What was up becomes down. What was down becomes up. So those are the two we're going to do today. Now that involves the students going through and knowing how to fill out a table. And this is, again, this is a foundational skill. They should be good at this point, but a lot of the students, they're just not putting in the work, they're not putting in the practice, and they're still struggling with this. So I'm going to work out this first one just to show you what's going on behind the scenes, and then realistically from this point we need to have this skill down because it's going to start slowing us down for the later chapters, and we want to get through some of these points because we don't want to fall behind for the end of the year. Our function f of x is doubling the input and then subtracting 1. So my input is listed over here. So if it says multiply it by 2, I double the input, then subtract 1. PEMDAS. So let's double negative 3. It becomes negative 6. Negative 6 minus 1 becomes negative 7. Okay. If I double my input, double negative 2 is negative 4. Negative 4 minus 1 is negative 5. Double the negative 1 becomes negative 2. Negative 2 minus 1 becomes negative 3. Double the input, subtract 1. 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 That's realistically how long this should take. Now, a lot of the students looked at that and they're like, what just happened? I have no idea what you're doing right now. Okay, let's go back to how do we build a table. Now, typically when we build a table, we haven't gotten to functions, but the functions work the same way as like an XY table. The X's are my inputs. The Y is the same thing as f of x, is my output. So if I have something like negative 3, negative 2, negative 1, or 0, actually let me do this in green. Might make it a little easier to see what exactly we're doing here. So negative 3, negative 2, negative 1, and 0. I'm going to write out this formula, and instead of writing the letter x, I'm going to plug what I need to use as my input in for the x. I'm going to substitute out the x, which means 2 times x minus 1. I'm going to plug that number in for the input, which is going to be my negative 3. Then I'm going to work it out. At this point, it becomes order of operations. So 2 times negative 3 is negative 6 minus 1. Negative 6 minus 1 is negative 7. That's where that negative 7 came from, is we're doing this process by plugging our input into the function and seeing what do we get as an output. What do we get as a result? And we do this to every input. We say 2 times that input minus 1, 2 times this input minus 1, 2 times that input minus 1. Every single time we take our input and we plug them in. So I say input them, negative 2, negative 1, and 0. Every time I just evaluate it out. 2 times negative 2 is negative 4 minus 1 is negative 5. 2 times negative 1 is negative 2 minus 1 is negative 3. 2 times 0 is 0 minus 1 is negative 1. That's where these numbers come from. I'm just plugging in the values and solving. So if I were to graph that, right now I have negative 3, negative 7. That's not on my graph, but this point is negative 2, negative 5, negative 1, negative 3, 0, negative 1, 1, 1, 2, 3, and 3, 5. Here are all the points of my original function, f of x. Now what I want to do is I'm going to be doing some sort of a reflection. Not exactly sure what kind of a reflection, but what exactly am I going to be doing? So let's take a look at, it says g of x is equal to negative f of x. Okay? Well, I need to identify what is my input and what is my output. So what I have right now is I have, okay, I need to figure out how do I get f of x, and then how do I make it a negative f of x? Because that's what it's telling me to do. G of x is a negative version of f of x. Well, remember, f of x, when we built our table, is just another word for y. It's the output. So what I'm doing with my new function is I'm taking my old function's output and making it negative. So what I'm going to do is I'm going to add on a negative to my y. Okay. Well, I'm not doing anything to my inputs, am I? Okay, cool. So if I'm not doing anything to my inputs, let's keep my same inputs. It's got the same inputs as before. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. I kept those. But my outputs are negated. So what does that mean? Well, I'm making that a negative, negative 7. In essence, I'm going to say I want to make a negative, negative 7. And what happens when we have a negative, negative? It makes it just a positive. So this ends up becoming a 7. What happens when I make a negative, negative 5? 5. Negative, negative 3. Negative, negative 1. And then at this point, it's a negative, positive 1, which is a negative, negative, negative. So quite literally, I'm going to take the f of x of my old function and negate it, which means change the sign. So what I wrote on here for the students today was I said, hey, negate the y term. And again, the verbiage that we're using is negate, which means to put a negative in front of. In this case, it means change the sign. Long story short, y is telling us how far up or down we go. So if I negate that, what that means is if I was told to go up, negating that means go down. If I was going down, negating that means going up. I'm reflecting, and I'm reflecting up and down. If I was going up, now I'm going down. If I was going down, I'm now going up. So let's see what that looks like. Okay. Now I could just graph this as is and just pop that on there, but I think there's an easier way to do it. If I look at each one of these points, well, this point, again, the left-right has not changed direction. The up-down has, again, because it's been negated. So I'm going to leave it on this line, but if it was down 5, I'm going to put this point up 5. If this was down 3, I'm going to put this point up 3 instead. If this was down 1, I'm going to put it up 1. If that was up 1, I'm going to put it down 1. Again, all I'm doing is I'm swapping the up-down direction. Those are my new points. So if I were to graph these with a line, this is my original graph, is this right here. So I've got arrow, arrow. And then this is my new graph. Right from here to here. Oh, just erased half the stuff on my board by dropping that. Okay. I can see, in fact, yes, I have. My green line is going up as I go over. My red line is going down as I go over. I've changed directions. What was up is now down. What was down is now up. Now, if you're graphing this, one of the things I told the students, if you're graphing this all in pencil and you have 2 gray lines, what's what? Which is which? If you're doing this all in one color, label your graphs. So right at the end, go ahead and put an f of x by the one that goes up. That's the original. And in this case, my new graph, we called g of x. That shows me, hey, look, I flipped it. Now, with a line, when we reflect it, sometimes students say, well, you just rotated it. No, we didn't. But we know that there's a reflection because they always cross on one of the axes, either the x or the y axis. So if I know up became down, I'm going to find the point where these 2 graphs touch right there. Whichever axis they touch at is the line of reflection. So again, my x differentiates between what is above it and what is below it. So it makes sense that if I flipped up to down, they cross it where those points cross. Think of like a mirror. You walk into a room and you're like, hey, there's a giant mirror here. How do I not walk into the mirror? Well, obviously I would see myself, but most of us would look at like the floor. If you've ever been in one of those carnival houses where you walk through the mirror maze, watch how people do it. What they do is they're looking at the floor and they're trying to see, okay, I see that there's a mirror there because I'm seeing my reflection touch right there. So they're looking for the lines of reflection, or they're looking for a reflected image on the floor. So if I see a reflected image right here, I know the mirror's right there. There's not a mirror up here, but right where those reflections touch each other, that's where the mirror is. Boom, right there. So I'm going to call this my line of reflection. Okay. Now similarly with this one, I'm not negating the output, I am negating the input. The x has the negative sign on it, which means I'm not going to keep the x and change the y. I'm going to keep the y and change the x. I'm going to flip it or reflect it, but in a different way. So let's see how it goes. Now I did pull a trick, and this is why I said I was a little alarmed, is I said, okay, I want you guys to fill out this function table. So plug in these inputs into f of x. And I gave them a few minutes to do it. Only a few kids in each class got it done. And the alarming part is, we've already done that. The answers were right here. We plugged in these inputs into the function f of x up here. I asked them to do it again. Some of them, most of them didn't really know what was going on. Little alarming, because we've done this a bunch. But let's move forward. When I plug this in, I'll get -7, -5, -3, -1, 0, 1, where am I? 0, 1, and 3. Not 0, 1. LOL. Copying down the table, can't even copy down the table right. Some of you should take for example from that. But, okay, so I've got my original table. Let's go ahead and graph it. It's going to look the exact same as my previous green line because, again, I'm starting with the same graph. I just want to flip it in a different way and see what does that look like. Okay? Well, if this graph, if I'm changing the x values left becomes right and right becomes left because the x values are what differentiates your left from your right. So, okay, if that's the case, I'm going to swap their orientation over here. I'll fill this in here in a moment. Let's see if we get it right. So if this was right 3, I'm now going to make it left 3. If this was right 2, I'm going to make it left 2. Right 1, let's make it left 1. This was in the middle. Let's leave it in the middle. This was left 1, I'll make it right 1. This was left 2, I'll make it right 2. Bet you those are the points I'm going to get on my table. Let's see. Well, in this case, if I'm changing my input and not my output, all I'm going to do is I'm going to keep the original output. -7, -5, -3, -1, 1, 3, and 5. I kept the output. What I'm going to change is I'm going to change the input. So let's go ahead and let's take each one of these, and I'm going to negate the x term. Negate the x term. So I'm going to make it a -3, -2, -1, -0, -1, -2, -3. So I get that. And lo and behold, every one of those red points is already graphed. 2, -5, 2, -5. I've already got that on there. 1, -3 is 1, -3. 0, -1, -1, +1, and so on and so forth. So let's take a look and see how this graph would look. I moved my line. And I moved it again. The whole point of a ruler is to keep a straight line. If you're moving the ruler, it's not a straight line. F of x. There's my original line, and my new line looks like this. But Mr. Johnson, that looks basically the same thing as the other one. This one is going down where the green one was going up, just like the last one. What do you mean it's different? Let's take a look. Where do these two lines intersect? Where does the reflection touch itself? Okay. It doesn't touch on the x-axis anymore. This one's touching on the y-axis, which again makes sense because the y-axis tells us right from left. The x-axis separates up from down, not what we flipped. This time we're flipping the left and the right. So in this case, if I were to think of where the mirror would be on this thing, the mirror on this would be against the wall. You're looking at the reflection. This laser beam that's going down looks like you're shining it through the mirror and at the floor right there, but really what's happening is it's actually shining at the floor behind you. You just think you're shining it through the mirror and down at the floor. But, okay, cool, line of reflection. Mostly what they're going to be looking at for is if we have graphed lines, like typically you're going to see examples like this already graphed, the student's going to be in charge of, at this level, where is the line of reflection? Okay, if there's a reflection here, they're touching on the y-axis, this must be a horizontal reflection. The x must be negated. That's really what they're asked to do. This one, they're touching on the x-axis, this must be a vertical reflection, therefore the y value must be negated. That's mostly what they're going to try and do. If not, they're going to have to translate some tables over. What would happen if I reflected it? What would happen if I reflected the x versus the y? That's their skill. So I'm going to go ahead, I'm going to pause the video. We're going to jump over to the other whiteboard and we're going to do stretching and compressing. So give me one moment. Okay, now that we're on the other board, this one, the stretching and compressing is a little intimidating for them because we don't really have any complex shapes to graph yet. We're graphing lines, and lines when we stretch or compress are a little difficult to tell apart. So the best way I can visualize it with them is with a rubber band. If I have a line with a slope of x, let's say it's a slope of 1/1. This is a perfectly diagonal line. and I take my hands and I move them together. What happens to the line? It gets flat. So as I compress it, it looks like the line rotates and becomes flat because this line goes on forever. But I know it becomes flat because I've compressed it. Not because I've rotated it, because I've compressed it. And likewise, if I take this 1/1 and I take my hands and I separate them, the line becomes much more vertical. This is not a perfectly diagonal. This is almost a vertical line because I've stretched it quite a bit. If I bring my hands closer together, I notice that the line becomes perfectly diagonal again. So if I have those points of reference, that's super easy. Okay, lift my hands up and down, looks like it's vertical. Bring them together, looks like it's horizontal. Because I have my hands as a reference. Most of the time with stuff like this, the students are stuck looking at a graph that's in a square. Okay, this graph versus this graph, well, obviously I've taken that line and I've rotated it. No, I haven't taken that line and rotated it. What I've done is I've taken this line and I have lifted the separation on it. And I'm like, oh, that's actually the line. So I haven't rotated it, I've just stretched it. And that's a really difficult thing for them to spot because it's a line. The easier thing is when we get to a later section and they have actual shapes and you can tell, hey, that shape isn't the same shape anymore because it's skinnier. So like if I have like a generic parabola, let's look at something like this. And I take the top of this picture and the bottom of this picture and I stretch it. What I'm going to notice is I'm going to have a shape much more like this. And you're like, oh, hey, that's been stretched. Somebody took that and pulled that apart because there's more to the graph. Right now when we're doing lines, like I said, best way is like, oh, look, it gets vertical, not vertical, vertical, more horizontal. Cool, so let's try it out. Okay, now we have a different function on this one that we're doing things to. I have one stretch and one compress. Now you'll notice that I'm only doing vertical stretching and compressing because with horizontal stretching and compressing at this stage, at this level with their ability to graph, they're not going to be able to handle it. So we're going to skip over that, come back to that later once we've covered some other types of graphs and readdress it. So right now, I'm taking my function and saying take the input and subtract 2 from it. Here's my list of inputs. Let me subtract 2 from this number. Let me subtract 2 from this number. Let me subtract 2 from this number. From this number. From this number. From this number. And from this number. Boom, there we go. I have all of my numbers popped in there. Now let's go ahead and let's graph it. Ooh, meant to get a bigger graph. So give me one pause. Let me reset this up a little bit. There we go. So I've got a slightly bigger graph because what we're going to do is after we graph this, I'm going to stretch this by a factor of 3, which means I'm going to take the distance of my hands and multiply by a factor of 3. So when I graph this, -3, -5, 1, 2, 3, 1, 2, 3, 4, and 5. -4, -3, -2. There we go. I have all of these values right here. Now, when I read this script, again, one of the big things I'm teaching them how to read the script, the new function is equal to 3 times the output of the old. F of x is the output of f. I'm going to triple it to get my new function. It doesn't say anything about the input, so I'm going to leave my input at -3, -2, -1, 0, 1, 2, and 3. I'm going to keep that. But the f of x, I'm going to triple. So I'm going to take the f of x, and I'm going to stretch it 3 times, which means that -5 is now a -15. -4 is a -12. That's a -9, -6, -3, 0, and 3. So let's see what happens here. So what was a distance of 5 now becomes 6, 7, 8, 9, doubled, 11, 12, 13, 14, tripled. So notice the gap between my axis got 2, 3 times as big. That's what happens when I said, hey, I stretched it. I took the gap and said, well, if you were this far down, triple it. So my gap of 4 became a gap of 5, 6, 7, 8, 9, 10, 11, and 12. My gap of 3 became 4, 5, 6, 7, 8, and 9. My gap of 2 became 6. My gap of 1 became 3. If my next point was on the line and I triple a distance from the line of 0, it stays 0. Now this one was 1 unit up. Instead of being 1 unit up, it is now 3 units up. And that's where all of these points come from. I quite literally took the distance down, tripled it, or took the distance up and tripled that. Let's see how we did here. Let's graph the green line. Popped off to the side there, but okay. That's my f of x. And now let's do the red line. Need a bigger ruler on this one. Apparently this ruler is too heavy to support its own weight magnetically. But okay, there we go. And now, yep, that's way too heavy. LOL. Okay, now we can see the big part and the hard part that students have is looking at that graph and saying, hey, that green line wasn't rotated. It's been stretched. Because again, our shapes are very, very basic. They're really designed to practice this, how do we stretch a table, and to practice this, how do I read a transformation. Looking at the graph, we're practicing it, but we're going to get better as we go on, which is why I'm saving it just for vertical stretching. So there we go. G of x. The next one, I'm going to build a table for f of x, and I'm going to compress it, which means I'm going to shrink it by a factor of 1/2. So the graph is going to become half as tall and half as deep. So let's go ahead and pop the first set of tables, which is just take the number and subtract 2. So subtract 2 from this, subtract 2 from this, this, and that. Bingo. And we've got that set of points there. Now, again, doesn't say anything about the input. The x is completely normal. I'm taking the output and cutting it in half. So I'm going to keep the same input I originally had. -3 stays, -2, -1, 0, 1, 2, and 3. I keep those. But what I do is I take all of these green points, and when I bring them over, cut them in half. So we're going to call this a shrink by half. I don't like using that word. I like compression, but I'm old school. So half of -5 is -2.5. Half of 4, half of 3, half of 2, half of 1, half of 0, and half of +1. Okay, that's how we stretch, or I guess we'd say shrink a table. If I were to graph these, again, visually I'd say, okay, that's 5 away from the axis, let's cut that in half. That's 4, cut it in half. That's 3, cut it in half. That's 2, cut it in half. That's 1, cut it in half. Half of 0, 0, and half of +1 is half. So we have our new graph right here. And I have my old graph right beneath it. And again, just pointing it out because it's very hard for students to see that this green line wasn't rotated just a little bit. It in fact was stretched. One of the ways we can try it out is, again, let's take a look. So if I take the two endpoints of my green line, this is 5 away down here. Half of 5 is 2.5. Half of, this looks like it's right around 3. Cut that down to 1.5. My rubber band is now completely over my new line. So that red line wasn't rotated, it was quite literally shrunk. If I look at this one, and I can't do it here because I can't go that high, I'm going to put it at 1, and I'm going to put it at my -5. Now if I stretch it by a factor of 3, -5 became -15, and then 1 became 3. Boom, my rubber band is right over where my line is. So it has been stretched, it hasn't been rotated. And again, if that's a little difficult, that's okay. Again, we're really practicing on how do we manipulate the graphs. If the tables and graphing the points is hard, maybe need to get some help. But if you're still struggling with this, that's okay. We're seeing our transformations for the first time. Let's cover the homework and see what's going on for this week. Okay, so go over this here in just a minute. Our 3.7 homework is on page 153. Originally, when we did the first half, they had numbers 1 through 8. There was no due date attached to that, though, because I said let's wait until we finish the section. So they should theoretically have that done. However, I'm telling you, if you've watched this far, do they have that done? Probably not. So they probably have to do that tonight. If not tonight, it's numbers 9 through 18. Do all of those. All of these are all due tomorrow. Hopefully, they only have these to do, in which case it's a nice light. That's a little 10 questions. That should only be about 10 minutes or so of work because a lot of it's just identifying what happened. That's all due tomorrow. This is going to be our schedule. So what we've noticed is that we had a couple days of practice, and this is going to be left up in the classroom and added to throughout the quarter because this is the entirety of quarter 3 all the way down to the exams on December 17th, 18th, and 19th. We've even got fall break worked in here. We just completed, I should put this right here, 3.7. We did our lesson, we did our homework. That's going to move us to tomorrow, where we're going to cover probably a little more practice. I don't know how we're going to do 3.8 and 8.3 because we have a test on this Thursday for the second part of chapter 3. Now, we noticed that anything in blue, if the students are absent, those were graded activities or graded work. So we had 2 Delta Math practice days that were graded 2 weeks ago. We had the PSAT, which was not graded, but that is something that we couldn't work around. We had a pop quiz last Friday that was graded. We had a practice on Delta Math this Monday that was graded. Anything that's in green was not graded that day, but they probably should make up that work. If it's something like review, we had homecoming and early release. We didn't actually do anything on these 2 days. That was a review day for them. This was a review day for everybody. This will be up in class along with some of the other things that we're doing. That being said, I'll see you guys tomorrow with 3.7. See how we do.